Hello, everyone, and welcome back to the Geek Nighter podcast. I am your host, Kaivalya Apte, and I am back with another very interesting topic to discuss on this podcast. Today, we are going to talk about profiling in general, how you can approach profiling, what does it mean, how frequently should you do it, some best practices, and some practical examples. To share all that knowledge with us, I have Richard, who is currently working at Datadog. And he has amazing experience with profiling, finding performance bottlenecks and working with really critical applications. So with this, I would like to welcome Richard. Richard, thanks a lot for joining us. Let's start with a brief introduction about yourself, your experience with profiling, and what you're currently doing.
Thanks for having me on, firstly. I'm currently working on Java profiling at Datadog. In the past, I worked on Apache Pinot briefly. Before that, I was at Datadog, so I went back to Datadog. Before that, I worked in finance in London for about 10 years, working on various performance-sensitive systems. Awesome. My experience with profiling, I suppose my excuse me. I suppose my experience from profiling, I started using it for performance analysis and kind of like live systems. And I've kind of just enhanced my knowledge since working at Datadog and on Apache Pinot.
Yeah, that's very interesting. And, in this episode, we'll try to see how we can also enhance our knowledge with profiling. But yeah, let's start with very basic. For our viewers who don't know what is profiling, what is profiling? What do we mean by profiling applications?
Well, I think the word profile comes from, it's very similar to the way you would profile someone's credit score. Mm-hmm. So is this person worth lending money to? Have they done this, that, and the next thing? Taking a profile is like getting a characterization of your application. So what is it spending its time doing? How much is it allocating? Is it CPU? Are we getting lots of CPU samples? Then maybe it's CPU bound. It's kind of like a deep characterization of the application.
Mm-hmm. Yeah,
and the idea behind it's supposed to surface information to you that you can do something about. That is, I think that's the main thing for anything that you have a profile. It's got to be useful. There has to be a so what. Okay. Once a user has the data.
Okay. Yeah, that's very interesting. So basically, when an application runs, there can be multiple profiles attached to it, depending on what kind of profile we are looking at. As you said, on CPU, on, let's say, thread utilization, on memory utilization, on different types of bounds that we have.
And the engines that actually collect these data, they're completely different. They work in completely different ways. So there's not just like a profiler. There's a set of engines.
That makes sense. So there's like set of engines which are running parallel to your application, consuming some resources of your application, and then pulling out some data which is interesting for you to understand some performance bottlenecks, right?
Yeah, exactly. And the overhead depends on what you're trying to do. So there are some profiling techniques which you could never do in production. There are some which are so cheap, they're much cheaper than things that. Nobody ever says how much does logging cost. Usually a lot more than modern profilers.
Interesting. So since we are talking about some resources being used by these profilers, one thing comes to my mind that, how frequently should we do it, because it has this cost attached to it. So what is your take on that? How frequently we should profile our application?
My take is, everyone should run continuous profiling. And rather than deciding whether to have it on or to switch it off, people, if they want to tune overhead, they should look at which data do they actually need. So, not everybody actually needs allocation profiling. Allocation profiling on some versions of the JVM is much cheaper. So, you can have a runtime check. At Datadog, we actually have that. So we don't want to we don't want to enable JFR allocation profiling except for on recent versions of JDK 17 because it has a rate limited sampler, which reduces the overhead and the size of the recording that we get from allocation profiles, and it's more expensive on old ones. So, it's more about how much data do you want, how much of a complete picture. But I think of it like an insurance policy. Most of the time, your insurance policy doesn't pay out because your house doesn't get broken into. But let's say you've got an application in production and something happens, or you make a change which you didn't expect to be expensive, or cause a problem. You've got some kind of high level metrics which say, this is strange. Should investigate that. But then it's very difficult to kind of go down from metrics unless you've got profiling on to go and look at the profile and see see the explanation of that that increased counter or gauge or whatever it is. So if you didn't have it on, then you couldn't do that. You'd have to be, which would you rather do? Would you rather download a profile and probably understand the problem within a few minutes and get the thing solved, or say, you'd start to kind of theorize about what could possibly explain this indicator, which is telling us that something's gone wrong with the application. How do we reproduce it? Do we actually have a staging environment which has reproducible load? Maybe this problem only presents itself in your production load, and it's difficult to generate the same data, or it could be a data dependent problem. And if you don't have the profiling, then you don't actually have visibility into what's happened in production. So I'd say it's like an insurance policy. And if you look at the cost for a kind of a minimal, JFR based or async profiler based continuous profiling setup, you're talking about well below 5%, typically below 2 or 3%. And that's not just like a made up number. I mean, that's based on measurement. These are pretty low overhead. And I always find there's kind of like a cognitive dissonance with people when they talk about profiling. They assume that profiling is going to be really expensive, and this conversation never even comes up with logging or metrics, which tends to be quite a lot more expensive than profiling. In my experience, anyway.
That's very interesting, and I like the analogy with the insurance policy. You pay a little premium, but you get a lot of benefits when things go wrong, and that's when it gets tricky. Otherwise, if everything is running fine, I mean, you have nothing to do, right? It's all working fine. But exactly. When things go wrong, you need all the visibility into your application, I think, and that's when continuous profiling makes a lot of sense. Just to understand a little bit more on this, so let's take an example of a heap dump, right? So I have a Java application. I want to have heap dump ready whenever there is some issue and I want it, right? So this continuous profiling, would it keep creating heap dumps and upload it somewhere, or how does it work?
No, so heap dumps are very expensive to produce.
Okay.
So I mean, what you actually have to do to create a heap dump is basically have to walk the object graph. So that's like a stop the world garbage collection essentially. So that's going to scale. I mean, if you only take live objects, that's going to scale in the size of your working set. And if you if you want to see garbage in there as well, then it's even more expensive. If you set the live property of the dump. So and there's another problem with heap dumps. So first of all, it's very, very expensive, and it's basically the cost is proportional to the size of the heap essentially. And it contains like the things you have in your heap. So that includes like people's dates of birth and their credit card numbers, and depending on what your application is doing, you probably are very, very limited, like whether you can actually look at that heap dump yourself in some organizations. You certainly can't send it to somebody like, if you, an engineer at another organization that you're using this, using their tooling, you almost certainly can't send them a heap dump because it's too sensitive. So there are kind of newer kind of technologies for actually being able to like profile and sample object graphs. So there's the JFR has the old object sample, which I don't believe it's that widely used because it used to be very, very expensive, but since JDK 17, it's been much, much cheaper to use. Async profiler has a live leak profiler that you can use, which essentially does the same thing and samples the object graph and looks for objects that it thinks are leaks. But it's very difficult to tell the difference between a leak and a cache.
Yeah.
It's almost impossible. Like you need to know as the application, you know where your cache is in the object graph. Whereas the profiler might not.
Yeah, that makes sense. So just want to take an example from my experience here. So there was let's say a memory leak, and sometimes our application would just crash with out of memory, and it will be a problem. And we didn't have the heap dump, so because it is expensive, as you said. And reproducing that was difficult because it was only happening when there were certain types of exceptions, and happening when those exceptions were in a high number, right? So it was some leak where in the exception handler or something that it was keeping the entire stack trace in the memory or something like that. How is this approach typically, right? Because I cannot take continuous heap dumps. I need to have that reproducible scenario and do that in QA and not in production environment. So how would you kind of approach this problem?
Well, I think you hit the nail on the head when you said it's difficult to reproduce because that particular behavior was like data dependent. So you actually had to get some data which led to throwing that exception, which took you down the code path where the memory leak is. So I wouldn't necessarily want to do that in QA. So I would want something on in production. So I mean, one thing you could do is basically listen to if you register like an MBean listener to listen to like the old the size of old gen after each old kind of stop the world collection. If you see that that's going up a lot over a long period of time, then you could basically like enable profiling within a Java agent. So you see that the heap is trending up, then you can put old object sample on, or basically activate JFR and activate its old object sample event. And then if you're actually allocating enough of these stack traces that you're describing in this exception handler, I can imagine like maybe it was like caching them somehow without meaning to. So a classic memory leak. Or, maybe you had a kind of like a dodgy key in a hash map that you were putting the stack traces in and it was never getting cleared out. Then old object sample would see that and it would start telling you, you have a lot of stack traces and they're referenced by this map. And then that map is referenced by your exception handler. And that would make that kind of sampling that part of the object graph and emitting that as into the JFR recording, which you could then go and look at, would basically nail your issue for you. There's another way. I mean, the way I used to do it, I used to work on an application which was like an in-memory database, and the way we figured out memory leaks there was we needed to differentiate between caches and memory leaks, and memory leaks did happen. And because the application was basically an in-memory database, like just looking for the heap going up wasn't quite enough because like we were storing memory, we were storing data on the heap. So looking at things like, JVisual VM had a tool which essentially allowed you to record the generation of objects. So then it would give you, so every time there was a garbage collection, it would basically, if those objects got moved from like one area of the heap to another, like they would get a counter bumped on them. And so then you could go and look at the distribution of those counters. So if you had a cache or like some storage, then what you'd see is you'd see like these objects just kept on getting older and older and older, and you'd create some new ones. The heap isn't the heap is finite, so
Yeah.
you'd have some very young objects and you have some very old objects. But if you had a memory leak, you generally have like a linear pattern, because every
Yeah.
time you interacted with, like the dodgy hash map, with bad keys, or the hash map that you never remove from because your code that does the removal just doesn't execute because you got a bug in your code.
Yeah.
You get a kind of a linear pattern. But I'm not aware of any tools except for JVisual VM that do that, and I think it's quite expensive to implement at the JVM level. So that's kind of like something that you do in a QA environment, definitely
Yeah.
not in production.
Yeah, absolutely. I think I was a bit lucky in my example because I could correlate it with the number of exceptions metric that I had.
Yeah.
So I not quickly, but I mean after spending some time, of course, because I was looking at other areas of where the problem could be. But then when I looked at the graphs and correlated the number of exceptions with when the out of memory happened, it was like clear that, okay, the exceptions are causing this. And then I could, follow the code path.
Yeah.
And then I figured out, okay, there is a known problem with this library that, we have to do certain things.
Nice. I mean, just kind of reacting to that. So we have something Datadog in our Java agent, which is an exception profiler.
Mm-hmm.
And the way that works, for your specific case there, because I've actually had a similar issue that I fixed with it.
Yeah.
The way that works is it basically instruments the throwable constructor, and that's actually very, very low overhead. So you only have like one class to actually go and instrument.
Mm-hmm.
So that's very quick. So you just do it at the start. And inside the throwable constructor, it basically, every time you throw an exception, it goes and checks with a rate limited sampler, like how many exceptions have I thrown? Should I record this one? And then at that point, it emits a JFR event if it chooses to sample it. And then you basically get the exception stack trace. How did you the trace? How did you get down to this exception? It'll basically put that into a JFR recording. And I find that this is really useful because a lot of the time I've actually found issues where exceptions have actually been swallowed, and you don't see them. They're not in the logs. You've just got no idea. Or maybe you have some kind of exception handler and it depends how that, maybe that's buggy, like in your case. So if you actually instrument throwable, then you can you can see things that the application would otherwise hide from you.
That makes sense. Since you've already mentioned JFR and JVisual VM, I want to talk a little bit about the tools that you would recommend for profiling. So I think there are two parts, right? As a developer, I'm just keen in understanding on how I can profile an application. I just want to do it on my laptop. And then there is the production use case where I want to do it with real applications, right? So I want to split it into two parts. And what is your recommendation? If I want to learn how to profile an application on my laptop, what tools would you suggest versus if I have to do it in production?
Yeah, I think twice about doing it on your laptop because your laptop, I mean, I've got an M1. So that's got a different operating system. It's got a different silicon to what we run in production.
Yeah,
and lots of things are different. I mean, it's got a different JVM. The code that gets generated at runtime is different. There's just so many differences. So it might not be that representative to do it on your laptop. But if you were, I mean, Async Profiler, which is an amazing profiling tool written by a guy called Andrew Pangan, who's kind of a profiling guru. That's a really great tool. It's got lots of it's got lots of engines in it. So the CPU, there's different timers for CPU. So there can be differences between depending on. I mean, if we get into profiling mechanics, we can cover that.
Yeah.
Wall clock, it's got locks, it can do instrumentation at the native level. It does lots of amazing things. Then built into the JDK, there's JFR. JFR is it does lots of things. It's more than just profiling. It's kind of like deep tracing. It's almost like an event framework where you have kind of like latency thresholds on things like, how long was a thread parked for, or how long did a thread wait for a monitor. You'll get stack traces on those if the wait was longer than a configurable threshold. There are lots and lots of events in there. It does allocation profiling. It does CPU profiling. It doesn't have a wall clock profiler. But there's more than you could ever need, and it will tell you what other processes were running on the machine. So that can be quite interesting. It will tell you what the environment variables were, if you which you have to be careful with because they can be sensitive. There might be things like passwords in there. But it just captures an awful lot. So that's very useful for your laptop. And if you then want to analyze those, Async Profiler can give you like a flame graph or a tree view, and you can just look at that in the browser. Or you can use the mode where if you put JFR into its command line, you can produce a JFR file, and you can analyze that as if JFR had produced it itself. And JFR files can be opened with a tool called JMC, Java Mission Control, which is free. It's open source. And that will show you all of these events. And some of them are like really arcane, and you'll probably never want to look at them, but it's got method profiling. It shows you a timeline view for what your threads were doing. Allocation profiling with flame graphs, and it's got everything that you'd really want in there. Then in production, I'd use JFR or Async Profiler. They're quite accurate. Async Profiler can do some things that JFR can't. JFR is generally better integrated into the JVM. It's very, very safe. So I mean, to do that in production, you need to have some kind of agent which starts a recording for you, which starts collecting events and instruments the right places in the JVM to collect information, and you need to be able to send it somewhere. So we're at Datadog, we do that. We send it via the Datadog agent, and that gets back to our backend, and then you can basically look at the data in our UI. If you were doing that without vendor support, then you could build your own pipeline basically.
Yeah, that makes sense. I've used Datadog in my previous companies, and it was pretty handy and pretty useful for such use cases. Talking about tools, I can get started with these tools with a sample application. But what I've seen, also I've experienced that, there's a lot of information when I get a profile of an application, and it might get overwhelming if I don't know the basics of profiling and the basic concepts, right? So what are some concepts that you would like to highlight when it comes to profiling that one should know before even starting around that?
I think it's important to understand bias. So historically, well, first of all, I mean, there are two kinds of profilers. There's instrumenting profilers, which basically insert kind of instructions like counters into the start and exit of all your methods, and they're very, very precise, but they produce they kind of perturb the application, and they produce a lot of overhead. And then you have sampling profilers. And what sampling profilers do is they have a mechanism, so they have a thread or some kind of mechanism for deciding when to ask threads for stack traces. So there are biases in that mechanism of asking the threads for stack traces in the first place. I'll get into those in a minute, but the more fundamental bias is basically safe point bias. So there are two kind of APIs that you can use to get stack traces from the JVM. There's get call trace, which is safe point bias. It It will only be called in a safe point. It's totally safe. It's in a safe point. But that can, if you do anything. So first of all, if you only take stack trace in a safe point, first of all, you only see safe points.
Yeah.
So that introduces bias into what you're recording. More recent JVMs, they have the JIT compiler does this thing called loop strip mining, which inserts safe points into long loops. So you have basically loops broken down into chunks, and so you'll get many safe points in the loop, and so you'll see more of the loop, and so your profiler will see within the loop where it might not have done before. It would have been at the back edge of the loop or the back edge of a method or wherever the compiler inserts the safe points. But if you do things in a safe point, then all of the threads are locked at that point. So if that takes extra time, then you're increasing your latency. It doesn't take much for, if you think about what the worst case scenario for actually producing a stack trace and recording it could be, then across many, if you have lots of threads, then that you can end up extending the safe point pause for quite a long time. So that's something to be aware of. So if you're using tools like JVisual VM, you have those issues. You probably shouldn't use them in production because you can increase your safe point pause time, and you're going to see less of the code. Now, the other way of doing it that JFR and Async Profiler do is they basically use async get call trace, which can only be called within a signal handler, and that means that you can essentially see the profiler can see anything. It just whenever the thread gets interrupted and it handles a signal wherever the thread was suspended, you'll see the program counter there, and then that program counter needs to get mapped back to like a line of code, and that itself introduces bias because it uses a mapping generated by the JIT compiler to map the program counter back to the bytecode index. And by default, you only get a bytecode index for safe points. Yeah. So the mapping's still biased. So one thing you can do is you can set if you unlock diagnostic VM options on your JVM, you can set debug non-safe points, which essentially instructs the JIT compiler to generate a larger mapping and to generate bytecode indexes for more bytecodes. And even that there are problems with it. There are bugs in it. There are limits to how good that mapping from program counter back to bytecode, to get your line of Java code can really be. So yeah, I mean that you've got to be aware it's approximate. Then there are different kinds of there are different kinds of schedulers for profilers. So you might be scheduling based on wall time, so like every 10 milliseconds, assuming that you're using async get call trace and you're doing this, you're sending signals to threads to capture stack traces. You could schedule them based on wall time. You could schedule them what one of the engines in Async Profiler. If you have perf events open set, if you have perf events paranoid set in your Linux distribution, then you can use a syscall called perf events open, and then you can ask perf to essentially give you a callback every time like 100 cycles has passed. Which is if you're doing CPU profiling, that's way more useful than wall time, because it's like cycles is what the CPU is. Exactly. That's the fundamental event of the CPU. And JFR doesn't do that. It does it based on wall time, and then so like every 10 milliseconds it sends signal. It sends signals to I think it's 5 threads, and if those threads aren't doing anything at that time, it just drops a signal. So you might get 0 signals. You might get 0 samples, or you might get 5 samples. Okay. JFR won't walk certain stacks, so you have when you have a boundary between Java stack frames and native stack frames, JFR just won't go beyond that because it's kind of dangerous to do it. There are ways you could crash a JVM if you go beyond that boundary, and so it just drops those, so you don't see them. So that creates a kind of bias if you're using JFR, and if you're using JNI with JFR profiling. So if a lot of the time is actually spent in native methods, then JFR just won't really tell you about them.
Okay.
And so if you're not aware of that, you can fool yourself. And I think the best thing that you can do to just like figure out whether a profile is worth looking at or not, and this is something that JMC presents to you, is look at the number of samples that you got. If you've got a high sample count, then you've probably got a good profile. If you've got a low sample count, then throw it away and don't look at it.
Yeah, that makes sense. And coming at a little high level, when I look at some profiles, right? So the commonly known concepts to like a Java developer, let's say, is like, okay, number of threads, then there is CPU cycles, there is memory, there is garbage collection cycles, and the class loading and all that. So looking at a profile, how can I make sense out of let's say the number of threads, allocations that they have, or the CPU usage, if that is the problem. So how would you kind of approach that using just looking at a profile?
So if it's a JFR, if it's a JFR recording, then I open it in JMC, and it has basically like a process view, which is like a timeline. And it will show you the CPU utilization along that timeline. So you can see whether it's like 0 or 100 or something in between. And then on that same time scale, it shows you where the garbage collections were. And if you see a lot of garbage collector activity, then you kind of this is one of the most common problems with Java applications. Like you see there are lots of garbage collection pauses. There's a garbage collection panel in there, and it basically traces every single garbage collection. So if you see, and so you've got the times of all of them. So if you see that you've got some really long times in there, then you're kind of starting to form a hypothesis that this application has a garbage collection problem. And you could certainly do something if you just improved it. And then you can go and look at allocation, the allocation profiles. And that basically gives you like stack traces of, and it aggregates them together into a flame graph of where the allocations were taken. You need to be aware when you look at allocations recorded by JFR, how they're recorded. So it doesn't record every single allocation. You need to, like the way that some people would record allocation is quite interesting. Basically instrumenting constructors, but that's a very, very disruptive thing to do because the JVM has lots of optimizations to do with like eliminating allocations. And those eliminations, they kind of depend on the JIT compiler figuring out that the object doesn't escape anywhere. So if you go and put something which records the existence of the object into the constructor, you totally neuter that optimization. So you get a completely different result. So what JFR has to do is it basically, like every time like a thread local allocation buffer, which is what new objects are allocated from, is retired, then it will record the allocation that actually causes that retirement. Or if an object is so large that it doesn't fit into one of those buffers, it has to be allocated outside the TLAB, it will record that too. So that really biases JFR's allocation profiling towards large objects. So most of the time, that's what you want to be seeing anyway. So that's good. You're not going to capture every single allocation with it, but I would go and if you're worried about like the GC time based on having looked at the previous panels in JMC, then it's probably the large objects that you're going to get bang for buck by do I need to be allocating these? So that's a good place to go and look. If the CPU is high, that could be because your garbage collector is running all the time, or it could be because you have like high CPU usage. You can go and look at the method samples there, and that basically gives you, it just gives you a flame graph of. If you don't know what a flame graph is, then a good place to go and find out about this would be on like Brendan Gregg's blog. I think he invented the visualization, but it's essentially just like an aggregation, like a tree, an aggregation of stacks. of stack traces. It'll give you can go and look at the widest method. What is it?
Okay.
Or something you might want to do, because a lot of the time there isn't just a widest method. That's when it's really easy and nobody's looked at the profile before. A lot of the time you kind of have like a death by 1,000 cuts kind of thing, and so you have a method that could be and it's basically scattered all throughout the leaves. So inverting a flame graph is to basically sum by the total time in the method is good, and you get that in the stack trace view. And then sometimes you'll find that you just need to go and make that method faster, or it's very unlikely if it's down at the leaves and lots of places that you can just avoid it being called. So your optimization is going to be to make it faster.
Okay. Yeah, those are very interesting pointers. I want to make it even a little more realistic, and by taking an example. So let's say I have a LSM implementation, like most of the modern databases also use that. So I was reading some research done by RocksDB that they were facing some write throughput latency, and it was because of thread contentions at different levels. So let's say we have this problem. I have implemented an LSM. And I'm looking at, write throughput being, having high latency. How should I go about the problem, assuming that, let's say, thread utilization or thread resource contention is a problem?
So I think if you profiled that with JFR, you picked up on contention. Depending on the kind of lock that's being used, you have latency threshold events, which are basically on like monitor requires. So if you're using like the synchronized keyword, then every time you call into something which is synchronized and there's a monitor to wait on, if you're waiting for long enough, then you'll get an event and it will give you the address, and it'll give you the stack trace, and that's actually pretty, like, where did the code that actually called this come from? Like, what was it? And that should mean something to you as an application developer, like, the writer of the code. You're probably not using synchronized because lots of people don't, but you might want to go and look at, there's a thread park event. So if you have contention, then threads will be parked. If they're parked for long enough, then you'll see them and you'll get stack traces for that. And so they need, but they might actually just fit under the threshold and you won't be able to see them. So one of I'd probably go for, so I'd look at those, but it's kind of like a wall time profiling kind of problem. And there's a difference between wall clock profiling and CPU profiling, which is that when like a thread parks, then the CPU profiler won't see it because it's not burning cycles, right? So if you've got, no matter what the engine is, actually, you're just not going to see it because if you're using perf events, then you're not increasing the cycle, so you're not getting the callbacks. So wall clock is basically like, what is this thread doing? I don't care what. Send the signal to the thread. If it's parked somewhere, it'll tell you it's parked. If it's burning CPU, then it'll tell you, oh, I'm in this hot method, in the middle of a loop. But yeah, so async profiler has a wall clock profiler, which is really useful for finding stuff like that. But like just like popping back up a level, because I kind of think of profiling as almost like the lender of last resort. So let's say that you haven't prepared to put your LSM into production, and you've got basically no observability. You haven't instrumented it yourself with the points that you know are important. Then use a profiler, and a good profiler, like a wall clock profiler, will tell you that thing that you didn't expect. There are always going to be things you didn't expect, so it's great to profile. But you can probably expect with an LSM that like the compaction is a rare event and it's very slow. So if I were to write an LSM in Java, I would probably want to put the compaction, I'd probably want to put a JFR event around the compaction. And I could put a latency threshold on that. So I get an event with like data about the compaction event whenever one of them is slow. So I can just go and look in the recording, almost like I just put a log statement in.
Okay. Interesting.
And a sampling profiler is going to miss that most of the time.
Okay. So I think it's so important to also know about the biases that you might have depending on what kind of profile you're using. And so, I've seen this like the thread park, thread is parked and all those kind of events in a profile. And I couldn't make a lot of sense out of it. But it depends on what kind of problem you have. Maybe threads are parked, but that is not an issue. Maybe they are parked and that is the issue, depending on the type of problem you are solving.
It's a very noisy measure, because a lot of the time threads are parked because you've got an over provisioned thread pool.
Exactly.
And they're just waiting on the queue. There's nothing in the queue, so they're just waiting. But sometimes it means you've got an LSM tree, which is you've got contention. So it's worth looking at. I mean, so the event has what they're waiting on. So if you see that it's waiting on like a queue, and you have the thread name and it's like request pool or whatever it is, you know what that means. But if it's actually like it's got like LSM in the thread name and it's waiting on like some condition object that you know the address of, the package, you can filter them down to something that's useful.
That makes sense. And that also highlights an important point, that you should name your threads just to know and, classify them. Otherwise, you would have no idea what is going on.
And I think it's one of the most important things to do, actually. And that's one thing that I really like about JFR, is it's so thread oriented. It has a timeline view where you can, like by thread, and you can go and look at the names of the threads. You can figure out loads of things from it. Like you can see that, is the thread pool for the requests, I mean, is it just over provisioned? You see a big block of threads with the same name, even if you've never seen the application before, they're from the same pool. And then you see like most of the time they're like a salmon colored, which means it's idle. It's green if it's on CPU. Well, the thread pool is too big, so one of the best things you can do is like just go and grep for that name in the code base and see how it gets sized. Maybe it's in a container and it's got a default value that doesn't understand like the C groups of them.
Exactly.
It's far too large. There's lots of stuff you can do with thread names. I think is really
really critical.
Yeah.
That makes a lot of sense. So great. And I think most of the applications that we work on typically use a lot of threads. There's a lot of IO happening, network calls and all that. So there's a lot of waiting. So you need to look at, the pool size that you have, and, if you are having some kind of contention. So it's really critical to name your threads. Moving to a different type of problem with the same LSM. So typically to avoid disk usage, or not disk usage, but disk usage, basically to avoid my call to go to the disk, I might use some data structures, let's say like Bloom filters, to figure out where it is exactly, if it's there or not. And let's say the latency that I'm looking at is mainly because of the disk usage, and it is not optimally looking at the Bloom filters, and it has to look at all the segments that I have, for example. This is the problem. So to address this problem and understand where the latency is coming from, how would what kind of profile should I look at typically for IO based latency operations?
Well, I mean, so Pinot has Bloom filters for kind of accelerating inquiries. So you basically like take a column, take all the values that has like a high cardinality ID, hash them k times, and then write them into the Bloom filter, and they will collide, and you'll get some false negatives. I would say, like, if you've got like a Bloom filter, if you've got a problem like that, profiling might not actually be the right tool. Because when you create a Bloom filter, you choose the false negative rate, and you can record that. So either you've chosen like a really, so either you've chosen a really ineffective false negative rate and you're hitting the disk far too much and you need to go somewhere else, and you're going to trade some size or numbers of hashes, so some CPU somewhere else when you're building, to basically have a bigger bloom filter or basically reduce the false negative rate. I think you should meter it. You should put something in your application where you have that if else. Like if we're in the bloom filter, then let's go down the fast path. If we're not, we're going to have to go down to the file system. So if you've got that metric in place, then you may never need to look at profiles at all, and you can just see, wow, so I thought that I had like a 1% false negative rate, and I'm actually up at 10%. Something's wrong here. So somehow, like maybe it's the data, like maybe the most common keys are actually always going down to disk, and that's really unfortunate. It's very unlikely to happen, but maybe it theoretically could happen. If you've got that counter, you can gauge. You can figure that out at an application level. But if you basically, like, let's say you've gone like out on a bike ride without a puncture repair kit, and you just don't have any metrics at all, and you just don't know it's related to missing the bloom filter, then you can go and look at a profiler. And I would go for async profiler. I wouldn't it's not going to take you all the way down to the disk, but it's going to take you all the way to the kernel. So long as you've got perf events paranoid set to like 0 or not 3, which is a default in Ubuntu, and it just completely disables perf events open, you will basically get events from perf which goes right down to the kernel, and so you'll get the names of the syscalls. So if it's Pinot does a lot of memory mapping. So if you're actually hitting the disk, you'll see some mmap calls there when you wouldn't expect to, because you'd be hitting the bloom filter. And then basically where you see that syscall, you kind of you walk back up the stack to your get ID or whatever the method is, and the further you get up the stack, the more application sense it makes. You get to the point where it makes sense. You get to the point where it makes sense to you, and then you do something about it, which is probably going to be reconfiguring the bloom filter so it matches more often. Or if you're not using mmap, you'll get different syscalls, but you will see there'll be in async profiler they'll be yellow, and you'll see these fat yellow frames at the bottom, and then you can walk back up until it makes sense to you.
Okay. That is interesting, and I think that's probably how it's best to approach that, because high level metrics is kind of cheap. You typically have them. You don't have to profile to figure out the problems. But if you don't have them, if you have no idea what's going on, even after looking at the high level metrics, then probably profiling is a good way.
There is an inverse problem to that. I mean, when I started working on Pinot, I was working with the people who built it, and they knew it inside out, and so they knew what all the metrics meant. And they're not that rigorously cataloged. So if you've got an incident, then you need to know what the metrics mean. So if you built them yourself, I mean, when I've built them myself, I found it really easy. I know what that metric means, what the name is, and I go and look at it. But so that was a learning curve for me, just knowing what all the metrics meant. But what I often did was, when I couldn't find a metric which made sense, which kind of explained the problem, I would actually just connect a profiler, and I would normally be able to work backwards to what the problem was. And sometimes I found problems that with my kind of focus on using a profiler rather than having in-depth knowledge of all of the metrics to start off with, sometimes I find things that people didn't know existed. So there's a bit of a duality there.
That makes sense. Coming back to the third example, and kind of my favorite, because I think every Java developer has seen an out of memory issues in their application. So let's say my LSM implementation is failing because of some out of memory. There is memory leak. I don't know. Maybe there is memory leak. Maybe there is cache. As we discussed, it's kind of difficult to understand if it's cache or a memory leak. So how would you typically approach an out of memory problem?
I think it depends how quickly you have to solve it. So, I mean, we talked about old object sample
Yeah.
earlier. There's heap dump on out of memory error. So you just take the heap dump
Yeah.
when it balks in the first place, and you go and look at that and
Yeah.
load it into mat, and you might actually find it.
Hmm.
If you can quickly figure out that you have a leak from either old object sample or from a heap dump that you got when it crashed,
Yeah.
then just go and look at it and go and fix a problem.
Hmm.
If you don't, then maybe try increasing the size of the heap, because sometimes it's just that you don't have enough heap for your working space. It's not a memory leak. It's just you're
Yeah.
not allocating enough heap. Yeah. So I think we already talked about I would enable that event old object sample, and that's going to load basically the dominant, basically a stack trace of the dominator graph of potential leaks into JMC.
Yeah. Yeah, I think the point you mentioned about, sometimes your application just needs more memory. So that does not mean it is having a memory leak. So it happened to me. I was just loading some data in a tree format in my memory, and I was facing out of memory. And then my first guess was, okay, maybe I have a memory leak because I have implemented it. Maybe there is some problem with it, right? And I just didn't increase the memory size. I was looking into the heap dumps and all that. I couldn't find anything. And then I just, increased my memory, and it was not going above that limit, which means it just needed that upper bound of memory. And that was easier to solve because I could just throw more memory at it. But yes, understanding that the dominating objects and, understanding the heap dump, I think it's critical for specifically, Java developers who want to, optimize on heap and, understand if there is a memory leak.
It's worth noting that increasing the size of the heap has drawbacks, right? So if you go above 32 gigabytes, then you get larger object pointers. So it's not until you get above 40 gigabytes that you actually get any more space for objects, because the size of all the references has doubled. And when you get to 40 gigabytes, you start to get returns. Lots of garbage collectors work much better on smaller heaps. So if you can keep the heap as small as possible, unless you're using like ZGC, which is explicitly designed for very large heaps.
Okay.
And I don't know if they've implemented compressed object references yet. Historically, I haven't really used ZGC very much, but when it first came out, there weren't compressed object, so it didn't matter. So having a small heap, you'd still get 64-bit pointers. But with most garbage collectors below 32 gigabytes, you get 32-bit pointers, and that actually makes a huge difference.
Yeah, that makes sense. And like fun fact, when I was working on an application, and Richard was actually supporting me on so it was basically Apache Pinot. I was just trying to test it, and I was facing out of memory issues. So I had 32 gigs already, and I wanted to increase to 64 gigs. And Richard mentioned exactly the same, that it might have other problems when you go beyond 32 gigs. So that is a very interesting thing. And talking about the the memory settings I might have for a Java application, what I've seen is understanding the heap requirement of your application is important, because that's depending on the type of application. If you can sustain some of the pauses that you have because of GC, I think it's not that bad. But let's say you cannot sustain the pauses that might have latency spikes in your applications, then the XMS and XMX value also plays a critical role, right? So correct me if I'm wrong, but if you certainly going to increase the value of your JVM, then it's best to have XMS equals XMX, like giving the max memory altogether from the very beginning, right? What is your take on that?
That's how I'd normally set it, because every time the heap grows, you have like a stop the world event to do that. And if you don't want any of those, then you need to set it to the same thing. I mean, but if you're running a desktop application, it's different, isn't it? Because the more memory you can give back, your application can give back, the better it is. So I wouldn't do that for like my IDEs or anything
Yeah,
like that.
that makes
But
sense.
yeah, for server application, I would figure out how much memory do you need and just give it that much memory and don't let it resize.
Yeah. Is there a way to so I'm just being curious here. So let's say I have a application, maybe I have a cache, maybe I like it's a very simple cache, for example. Um, how do I do a rough calculation of what kind of heap size do I need? Do I just have to run that application and look at it, or how do I go about it?
I think just running the application and looking at it is normally the best way because
Yeah,
there are just so many layers that can interfere with things. And if you start getting
exactly.
into like, I mean, I talked about escape analysis and like just eliminating allocations altogether. If you don't take
Mm,
that into account, you get the wrong number. And so measurement's always the best thing, but it's kind of
yeah,
time consuming. And I think it's important to do kind of like napkin, like back of the envelope calculations.
yeah,
So I mean, the way I would do that, I mean, so normally with a cache, you have like a maximum size, which should be like hard configured. Otherwise, it's not really much of a cache.
yeah.
If you and you can use a tool from OpenJDK called Java Object Layout or JOL. It's just a library that basically instruments uh, it kind of knows, not instruments, but introspects the class layout and the object graph.
Yeah.
And so you can basically calculate the size of your objects with that. And so if you know what the maximum size of your cache is, and let's say they're shallow objects and they just contain like primitive fields, or strings of a size that you can predict, then you can basically calculate the average size of an object like that and do a back of the envelope calculation based on that actual size.
Yeah.
But that depends on the size of your heap, of course, because it depends on the size of the pointers. So you're still getting back towards measurement, but I think for a back of the envelope calculation, you could inform it with like knowing the size of the objects and then multiplying them by how many you think you should have for a given throughput or for a given maximum cache size, and you can get you
Yeah.
can get a rough number like that. But I'd still go for measurement.
Yeah. That makes sense. Talking about your experience, can you share like a couple of examples where profiling really help you figure out some performance bottlenecks or figuring out some issues with the applications?
Yeah. So I think it's best to well, I mean, one from Apache Pinot would be good because it's open source and I can
Yeah.
just talk about it. So I mean, just to give an example, that it's like I think sometimes there's a bit of fear, uncertainty, and doubt about profilers, and that use profilers to find like really hairy, complicated problems that are really complicated to solve. No, it's not really like sometimes like it's just like API misuse, and
Mm.
that's like you can make really basic changes. So I got a profile from an Apache Pinot customer. They were using regex-like, and if you have the right indexes, then Apache Pinot will basically use indexes to satisfy a regex. So
Yeah.
this is a query like select star from table where text column is like this regular expression. Um, it will use indexes if you have them, but there weren't indexes, and then some of the time it's actually better not to use those indexes because of the way like the Lucene implementation was implemented.
Hmm.
And you can do better with a dictionary and then running the regular expression scan on the dictionary. So the dictionary has all the unique string values. So if you have like a low cardinality, then you can basically go over the dictionary,
Mm.
compare the regular expression against each value like once, and then go to the column, decode the dictionary value, and check if it's in the set that you collected when you were scanning the dictionary. And so this was allocating like a lot of memory for queries, and these queries were quite slow. And it turned out that like the Pinot implementation, just the operator doing this dictionary scan wasn't calling reset on the matcher. So with the
Mm.
Java regular expression API, if you're on the same thread, you can just call reset, and then you don't have to like reallocate the storage for the automaton inside the matcher.
Yeah.
That saves a lot of memory. So it was just like a one-line fix, and it's like 25 gigabytes per query is gone. And that's knowing that in Pinot, an operator will have a match. Has basically for a given segment, it executes on the same thread, so it's fine. In general, you probably couldn't do that, and you'd want to get a new matcher each time if you don't know what the underlying thread model is. But in Pinot, the underlying thread model was there, and so we could just save all this memory, and it was a really, really simple fix. I could give another example from Pinot. I mean, there was one interesting one that I in a backend service at Datadog, which I can talk about without revealing very much, but we were calling a compression library, and compression libraries often have a JNI implementation and a native, a Java implementation. So, like if you look at like the LZ4 library, it will have like fastest instance, which generally will give you JNI. And then like fastest Java instance will generally give you something implemented in terms of unsafe. And then fastest safe instance, which is just like vanilla Java. And so we were using one of the implementations which used JNI for very short inputs. Yeah. And the data that was being allocated, the data that was actually being decompressed was actually allocated on heap. So when you use JNI with heap objects, you have to enter like a JNI critical section. Yeah. So you see in the stack trace, if you're using like async profiler to find stuff, you'll see like JNI get primitive array critical. And what that basically is it's like a lock. If you can deadlock in JNI if you're inside a get primitive array critical, and then you call it another one, and then if you don't release it, then you can deadlock the application. None of those things were happening. Like the compression library was correct. It was just the way we were using the compression library. So we got a significant CPU saving just by spotting that one stack frame. Oh, okay, let's change it to the unsafe version. And that was worth 5%. And the other thing is that get primitive array critical for a lot of garbage collectors actually blocks the garbage collector. So correlated with that, we actually got a reduction in GC pause, which you'd never have looked at. Yeah. It's just like you remove this one thing, and you probably it's JVM trivia, but not that many people know that one frame blocks the garbage collector. Garbage collection wasn't really a problem, but we got an improvement just by changing this one thing.
Yeah, very interesting. We talked a little bit about the some of the best practices, like naming threads and having the good understanding of high level metrics, and using that as the first approach. And then if you don't have any understanding of the metrics at high level, then you can go for profiling. And then running continuous profiling is a good thing. It's like we compared it with the insurance policy. What are other best practices that you would like to highlight for developers like me who are developing Java applications and are interested in profiling?
I think we've mostly talked about it. One thing I would say is that most of these tools, they have overhead and accuracy dependent on the number of threads. Yeah. So if you want to do wall clock profiling and you've got like a gazillion threads, then you can't send signals to all those threads because it's just the overhead's enormous. Yeah. So you have to send signals to a subset of the threads, and the more threads you have, the less accurate it is, because you're going to have to upscale by the ratio of the number of threads you signal to the number of threads you have. Yeah. And you don't want the profiler to tell you that I had this thread pool with 10,000 threads in it, and only 2 of them were doing work. And most of the time, you're going to see the ones which weren't doing any work, and they're just waiting. So that kind of destroys the value of that tool if you have too many threads. And like with monitoring tools in general, lots of them use things like thread locals. So if you have lots of like old school like physical threads, then these tools can get more expensive in general. Like they'll maintain things like stacks per thread, and I go for if I was going to say something simple, just think about how many threads you've got.
Yeah. Okay. Makes sense. What are the limitations that you see current tools for profiling applications have, and what's coming up in future? So talking about like Java, there's Project Loom, there will be like virtual threads, And I'm not sure how well the current tools would support that. Would that be even compatible, or they need to change? Or so, what is your take on the future of profiling?
So JFR, I believe a lot of work has been done to make sure it works with Loom, and
Okay.
in some ways, Loom gives you better better profiles, assuming you have a profiler which knows how to deal with the virtual stacks, because you get synchronous code again. Reactive frameworks make things quite hard to profile because you have you basically break all your work up and you scatter it across threads. You don't have like causality anymore. So stack trace gives you causality, but reactive kind of, it's very difficult to like reassemble stack traces across threads when you submitted work across threads. So it's possible, but none of the tools do it. So I mean, the limitations. I think the limitations are really overhead. It's like how much can you really signal?
Yeah.
How many signals can you send? Right, and it's quite an expensive thing to send a signal to kind of pause a thread. Within a signal handler, you can't allocate, so there's a limit to what you can do. Within a signal handler, you have to write code, like native code, in a very kind of particular way. You know, the more threads you've got, the less valuable wall clock profiling is. I think one of the future things that's coming up, and there's a PR in async profiling. We've kind of implemented something similar at Datadog. It's basically contextual profiling. So imagine that you have like tags associated with a high level request. So imagine, let's go back up a level. Imagine you have like a web server, and you have different endpoints on that web server. Maybe it's like monolithic, or maybe you have like a very kind of you have a microservice, but it has like a health endpoint. You don't really want to see the profiles of the health endpoint.
Yeah.
And you want to basically filter everything in a profile based on like the URL. You know, what's the expensive bit? Is it updating the user, or is it getting the user? You know, like what is the most expensive request? Imagine, so a lot of the time you just get like a monolithic profile and you can't break it down. It's just that's everything that happened. You don't know what the workload was, and you want to break it down somehow, filter it. Being able to label profiles like as a physical data structure, just like a sequence of events. Being able to label those events, saying this event was caused by work associated with get users, and this event was associated with work caused by create user or whatever whatever the endpoint was. Then you can basically say, I only want to see the profile for create user. Okay, that's only like 2% of CPUs. That's only 2% of the samples. From that, you can infer 2% of CPU time if you've got a lot of CPU time. Oh, but the really expensive one was get users, and that's because, and you go and look at the stack trace, and you can go and optimize that flow. So you get more context in your profiles by the ability to label. And so that's something that's coming to Async Profiler.
Yeah.
That is something that I think that lots of people get a lot of value from.
Yeah, I can imagine. Yeah. So having like a more granular control without increasing the overhead is the challenge that we are trying to solve, right?
Yeah, I mean, just being able to filter. So you have all of these stack traces, just being able to filter back to something that means something to you.
Yeah. Okay. Using the labels.
Yeah, because it's kind of hard to like. You can figure it out from the stack traces because you'll have the method names in there.
Yeah.
But it's kind of difficult to if you have like really generic method names. So you have like that's when the profile gets difficult to read.
Yeah. Yeah.
Because a lot of the stack traces get munged together, and you don't really know why or which one the slow child was. But if you have the ability to filter because you label all the events, then you can say, oh, okay, so this is something to do with create user. So I could, set up a load test just for that one endpoint, and I'd get a similar profile to filtering it, and I can start to optimize it.
Yeah, absolutely. Great. This has been an amazing discussion. I actually learned a lot just by talking to you. how can I gain more knowledge? If even for our viewers, what are some resources that you would suggest to learn more about, these concepts and profiling in general, and what's happening in the profiling community and all that?
I'm not really aware of any books. I'm not much of a book reader when it comes to technology,
Yeah.
but I read lots of blogs. I also, blogs. There's Brendan Gregg, who created a lot of the concepts. There's Marcus Hurt, who created JFR and is director of profiling at Datadog. To know about Nitzan Wackart writes a blog, which I think will be in the links. He's written a lot about profilers, and he really kind of evangelized the whole safe point bias thing that we talked about.
Yeah.
And for kind of like JVM knowledge, I find Alexei Shiplev's blog is the best one.
Okay. Yeah, very interesting. So I'm going to add all those links in the video description, so it's accessible for our viewers as well. Great. I believe we have added a lot of value with this discussion to folks who are really interested into profiling applications, understanding performance bottlenecks, and basically improving the applications in different aspects. So yeah, thanks a lot, Richard, for joining us and sharing all the insights that you have on profiling. I think it is really helpful and it's going to add a lot of value. So I hope you also enjoyed the discussion, and
definitely.
I'm really looking forward to collaborate with you more and learn from you. So thanks a lot for doing this.
Well, I hope this was useful for people, and thanks for having me on. I've been watching for a while, so I'm really flattered to be on. Thank you.
Awesome.
Thanks for your time.
Thank you.